Hey guys, welcome to Electronics. I'm Gregory, and in this video you're going to understand how phase noise measurement works using the cross-correlation method, allowing the measurement of phase noises lower than the analyzer phase noise. Very interesting. I also wrote an octave simulation that virtualizes the measurement using the cross-correlation, simulating an analyzer measuring an oscillator, and we are going to study the differences and the improvements in phase noise measurement using the cross-correlation method. Take your coffee and come with me. So let's imagine that we need to measure the phase noise of an oscillator, and it can be any kind of oscillator. In this example here, let's think it is a radio frequency oscillator. And before we go to the real oscillator here, let's remind ourselves that an ideal oscillator, a mathematical oscillator, will generate signals, will generate an output frequency very precise without perturbations in amplitude and in phase. This is why the output spectrum or the power density in the output of an ideal oscillator is a single tone, a very pure tone, only a line in the spectrum, meaning that we have energy only at a single frequency. But of course, a real oscillator like this one here is not like an ideal oscillator. It has phase noise. So if we imagine that the real oscillator is outputting a sinusoidal signal, the phase of the signal is wiggling around a little bit in a random fashion. So as the phase is wiggling around, this degrades the oscillator in the sense of a time base, in the sense of a frequency base, because the noise imposes uncertainty. And this is very interesting. Actually, a real oscillator will have energy spread around the main tone. And this phase noise comes from different sources inside the oscillator. It can be supply noise, modulating the oscillator parametrically, changing the parameters of the oscillator in real time, so the phase of the oscillator is moving. It can be flicker shot noise in the active device, in the transistor. And it also can be thermal noise that can modulate the capacitances around the oscillator. And as the capacitances are changing, we are also deviating the phase in real time in a random fashion. So the phase noise comes from a combination of a lot of factors inside the oscillator, and the power in the output of the oscillator will spread around the main tone because now we have uncertainty in the phase. We added entropy in the signal, and of course, if we have entropy, we have bandwidth, because now the signal has information. The information is random because it is the noise, but we can think of the noise as a modulation source to an ideal oscillator. And now we understand why the energy spreads around, because we have the ideal oscillator model, the mathematical oscillator, and we can model mathematically the behavior as a phase modulator in the output of the oscillator that is modulating the phase of the signal, and this is a multiplicative effect. Is the multiplication is a non-linear effect, and the noise floor can be modeled as an additive effect, adding noise in the output. So we have modulation, multiplication of the signal actually by the noise, and an additive process that's creating the noise floor in the output of a real oscillator model. This block diagram here is a simplification. It is a little more complicated because for a deep analysis we need to consider the phase modulation noise and the amplitude modulation noise, and these two mathematical noise sources can be decomposed in quadrature and in phase parts using imaginary mathematics, but this is not the idea of this presentation here, so we can keep it simple. So let's try to measure the phase noise of this real oscillator here. We have an oscillator on the bench, and we need to measure the phase noise. And guys, if you want to learn more about phase noise measurement and its use cases, you can click in the link in the description. Here on the Keysight Use Cases website, we have a dedicated page about phase noise measurement. Keysight mastered the cross-correlation method, and they have a very good application note about this that explains in detail all the different methods for phase noise measurement. And actually, I used this PDF, this application note, as the reference for this video. To learn more about phase noise measurements, use the link in the description and take a look at the Keysight Use Cases website. So let's imagine we are trying to measure the phase noise connecting the oscillator that you have in the input of a spectrum analyzer, and here I draw a topology. This is a simplified topology, but it will work as an example here. So inside the spectrum analyzer, the problem is that actually the spectrum analyzer also works using oscillators inside. And of course, all the oscillators of the spectrum analyzer are real oscillators that also have phase noise. So here I draw the time reference, the frequency reference of the spectrum analyzer, and you can see that I draw it as another real oscillator because the spectrum analyzer also has a phase noise floor. And of course, we cannot measure a phase noise that is lower than the phase noise of the spectrum analyzer. So the phase noise of the measurement equipment is the limit of this technique here. The specifications of the measurement equipment limits what we can measure, and this makes total sense. So actually, if we try to measure the phase noise using a standard spectrum analyzer, we are going to capture this red noise profile here that is higher than the oscillator noise, because here we are measuring the combined noise profiles of the DUT and also of the measurement equipment. We can see that the true DUT noise is lower here, and of course it is lower than the noise floor of the measurement. And of course, if we have a very good spectrum analyzer that has a phase noise at least 10 dB better than the phase noise of the oscillator you're trying to measure, it's gonna work because the spectrum analyzer has a phase noise lower than the oscillator you're trying to measure. But for measuring very clear oscillators, this measurement setup becomes a problem. But we can solve this problem with a very elegant solution. And this solution here is very beautiful because it is actually an statistical approach. It is a statistical solution. We can have two spectrum analyzers. We can have two measurement devices. So now we have measurement equipment A and measurement equipment B. Yeah, this is actually two measurement equipments. They can be inside the same box, but we actually have two paths of measurement, and the two paths are uncorrelated. So the noise introduced by the equipment on the top is uncorrelated by the noise introduced by the equipment on the bottom. And the only correlated signal that the two equipments are seeing is the DUT, is the oscillator we are trying to measure. Of course, here we added a splitter, a power splitter that is splitting the power between the two measurement equipments. But this is the only signal that is common between the two measurement equipments, and this signal goes through the measurement path A and through the measurement path B. Going back to the other slide, we can see that this measurement equipment model here has an attenuator in the input that is adding thermal noise. Thermal noise is a totally random variable. And as this is a very simplified model, we have a down converter that feeds the ADC. The ADC is digitalizing now the data, all the signal here, and the spectrum analyzer is performing an FFT of the signal string, of the data string, to plot the power density here on the output. This is a very simplified topology that's missing a lot of things here, and it is actually missing a fundamental blocks here. It can be working in quadrature, it can be up converting the signal to an IF and sampling the IF. There's a lot of different ways to digitalize a signal to create a spectrum plot, but it doesn't matter for this presentation here. But if we have two measurement devices, two measurement equipments, we can add a block here that will perform a correlation between the two measurements. And this is really beautiful. As the noise added by the two measurement equipments are uncorrelated, and the only correlated signal that travels through the two measurement paths is the signal from the DUT, we can perform a correlation in the output to enhance the correlated signal and to reduce the power of the uncorrelated signals, of the noises. So actually doing multiple correlations and averaging the results, we can reduce the noise level below the noise floor of the measurement equipment. This is very beautiful. We can actually measure a signal that is lower than the noise floor because we are correlating two measurements, and when we correlate an average, we enhance the correlated power, the signal we are trying to measure, and we decrease the power of the noise. So take a look at this, guys. This is very beautiful. I reduced a little more the equipment here. So now we have all the front end stuff here in this block and the FFT for equipment A and for equipment B, and here is the oscillator. And here I simplified a lot the math to become simple to understand, but I think that it's still very interesting. So take a look at this, guys. We have here on the input of the two measurement equipments the signal plus the noise of the signal. So let's imagine that this description here, this mathematical description, is actually the ideal signal plus the noises that are imposed. And we see it here, signal plus signal noise. This is a signal in the time domain, of course, because we live in the time domain in the world. But when we apply this measured signal to the FFT, we can translate the signal to the frequency domain. So in the output of the analyzer A, we have the signal in the frequency domain, uppercase S, the signal noise in the frequency domain, plus the measurement equipment A, noise in the frequency domain. And on the bottom, we have the signal. Of course, this is the same signal and the same noise. This is the correlated part. And we also have now the measurement equipment B, noise. The noise added by the equipment on the bottom here. If we imagine that the FFT is a filter bank, the K is indexing the filter bank of each band in each bin of the FFT. And look at this, because this is very beautiful. In the frequency domain, this is the definition, the mathematical definition of the correlation in the frequency domain is the multiplication of the signal A by the conjugate of the signal B. So you have two signals, we multiply the signal A by the conjugate of the signal B, bin by bin of the FFT. And of course, if we are coming from the time domain, we need to first apply the FFT to the time domain signal A and the FFT to the time domain signal B. And this is exactly what the measurement equipment is doing. It is applying the FFT to any signal that is present on its input. So look at this. We have the signal plus signal noise plus the noise of the measurement A times the conjugate of the signal plus the noise of the measurement B. And if we multiply these terms here, we are going to see that we have 4 terms in the output. And look at this, because this is very, very interesting. Remember that always that we multiply an imaginary number by its conjugate, the output is a real number. This is only mathematics. Always that we multiply an imaginary number by its conjugate, it becomes a real output, a real number. And this is the first term here. So look at this. The input signal that is common to the two analyzers will be multiplied by itself and will become a real number. But all the other terms that are multiplying by a noise will become a random number, an imaginary number, a vector that is pointing to a random direction. It doesn't matter if we are applying the conjugate to the noise. We have a noise is a random vector. We are applying the conjugate. It doesn't matter. We are multiplying to the signal in this case here. Is this cross multiplication here? The signal from the analyzer B times the noise of analyzer A. It will become a random vector. This will become a random vector. Noise multiplied by noise will become a random vector. So look at these guys. All the noise terms are random, but the signal is multiplied by itself and it's becoming a real number. So if we make one correlation, one step of correlation, store the result. Now we make another correlation, another correlation, another correlation. We are going to have different sets of imaginary numbers, of vectors pointing to random directions. But if we average all the correlations, all the noise terms, all the noise vectors from all the correlations will null, and only the real number, only the output from the multiplication of the correlated part of the signal will enhance itself. So look at this, guys, because this is very beautiful. And remember that this is done for each bin of the FFT. So each bin of the FFT is an imaginary number that is actually a vector that is composed by these 4 terms here. And we can see it here. Look at these guys. Let's imagine that we are looking to the one of the indexes of the FFT. It doesn't matter what is the index. We have taken one index to look, and we have here 4 correlations, 4 measurements. Look at this. In the first correlation, these are the 4 terms of the correlation. We have the real part, that is here, is the correlated part. And we also have 4 vectors, 4 terms that are vectors pointing to random directions. When we make a new correlation, the signal that is correlated will point in the real axis, but the random vectors are pointing to different directions. And we make a new correlation, and this happens again. And this happens again. And this sequence happens in parallel for each bin of the FFT. So if we average the results here of 4 correlations, of course, all these vectors, all the vector terms that are pointing to random directions will collapse to a lower value because they are pointing to random directions. They will null, and only the signal that is pointing to the same direction, only this term here will be enhanced. So if we look at the output of the correlation, we have a vector, a value, an imaginary number for each beam. After the average, all these vectors are more or less pointing to the real axis because all the noise was reduced and the energy of the correlated part, the signal we are trying to measure, is enhanced and pointing more or less in the y-axis, in the real axis. Of course, if we increase the numbers of measurements before the average, the number of correlations before the average, the output vectors in the correlation beams will point more and more to the real axis because all the random terms will collapse more and more. And now that they have the correlation vector, there is a vector in the memory of vectors. Each beam is a vector, and all these vectors are pointing more or less to the real axis, and they are proportional to the power in that beam. We can take the length of each vector, of course, and apply a log function, and we can directly plot the spectrum. And this spectrum here has a lower noise floor. And as the number of correlations in the average is increased, the noise floor can be lower and lower and lower, even lower than the noise floor of the measurement equipment. And of course, to plot here in dBc, in dBs relative to the amplitude, of course you need to make a little more math because you need to subtract the peak power, but it doesn't matter here. The main idea here is that the FFT outputs are correlated and average, correlated and average, correlated and average. And as we make more and more averages, all the noise terms, the noise contribution starts to collapse to zero, and the real correlated signal that is proportional to the power of the input signal in that frequency beam is increased and enhanced, and in the end we have this vector of vectors, this vector of imaginary numbers that can be directly plotted as the spectrum of the input signal with a noise floor better than the measurement equipment. This is very, very, very interesting, guys. And we have, of course, a proof that this works. So I first create a signal at 10.7 megahertz. Let's imagine that this is an oscillator running at 10.7 megahertz. And we can see that this oscillator here, in blue, the signal under test, this oscillator here has phase noise. It has its power spread around the main tone. And here I'm simulating an up conversion inside the analyzer. So let's imagine that the analyzer here, this virtual analyzer, has an up converter section inside the front end, and this up converting process is adding its own phase noise. So here we have the same signal, but now in a different frequency. Look at this. This is for simulation, so it becomes easier to understand. We can see that the analyzer is using a 22 megahertz IF, and this signal inside the analyzer has a greater phase noise because now the analyzer added its own phase noise to the signal it's trying to measure. And if we plot here, guys, look at this. Here we have the phase noise in dBc, and here is the offset. Here is the distance from the main tone. So actually, when we look at this plot here, we are looking at the left side of the signal. You can imagine that the main tone is here in the side, and we are measuring the power on the side bands. So look at this. This blue phase noise profile here is the noise of the oscillator we are trying to measure. But look that inside the analyzer is looking to the orange signal that has a greater phase noise because the measurement equipment is corrupting the measurement. And we can see that if we apply the X correlation, the cross correlation, using 200 averages, we get this purple line here that is approaching the true DUT phase noise profile in blue. Very, very interesting. Let's try to increase the number of averages to, let me think, 600 averages. You can see the progress of the correlations here. We are doing 600. Okay, it's done. And look at this. Man, this is so nice. Look at this. Look how now the correlated measurement approaches even more the true DUT phase noise. And if we keep increasing the number of averages, the correlated measurement will approach the true signal we are trying to measure. And guys, what I did here is that I also plotted the phase noise of a time domain average of one spectrum analyzer. Only one, because I'm sure you are thinking why you cannot get one spectrum analyzer or one oscilloscope and make a lot of measurements in the time domain and average all the measurements, and after this plot the spectrum to get the real phase noise. This will not work. Think a little more. If we have only one measurement device, we cannot uncorrelate the noise from the signal we are trying to measure. This is impossible. We don't have enough information to make it work. And of course, if we try to make averages and averages of a time domain signal, the noise will totally disappear. Think a little more, because we would not be uncorrelating the true noise of the signal from the noise of the equipment. We would be averaging also the noise of the signal. So of course, a time domain average, as the average size is increased, this noise floor here will tend to zero, because we are averaging the noise of the equipment and the noise of the signal source. We are not uncorrelating the two. So look at this. This yellow line here is bullshit. It is not a measurement. And you can see that this phase noise of this measurement here is lower than the true noise of the signal source, because we are also averaging the noise of the source of the oscillator. This is the big difference. This is the big leap in thinking of using two equipments and a correlation that provides enough information so we can uncorrelate the two noise sources. Well guys, I hope you enjoyed this video. If so, subscribe to the channel and give it a thumbs up. And remember to take a look on the Keysight application note about phase noise measurement, link in the description. I see you in the next video of All Electronics.